Okay. Okay, so this is vector dA. And then what I need, you see, is vector BC. I use the same idea here. So vector BC is the final point, which is C. And if you see the coordinates of C are given in the problem to be 1 and 1, minus the initial point B, which is minus 3 and 1. So then I do component-wise again. So it becomes 1 minus minus 3 for the first one, 1 minus 1 for the second one. And then what happens, it becomes, yeah, that is very coincidentally, they are equal. Yes, I have done everything probably. So these two vectors are actually the same vectors, yes. That was a coincidence here. So because 1 minus minus 3 becomes 4 again, and then 1 minus 1 becomes 0. So this means that my vector BC was coincidentally the same vector as dA. Yeah, that was not my intention. I was so unlucky that these random numbers gave the rise to the same, but it doesn't matter. So, but then we go and calculate this number here. Sorry, this vector here. So 3D, so I would write therefore. It's always good to write words to make it clear for the people who are reading your work. So 3dA minus 2bc. Let me pretend that they are not equal, because when they are equal, actually, I can write one of them. Yeah, 3 of dA minus 2 of dA becomes 1 dA. Yes, okay. So what happens here, I will get 3 times 4, 0. This is the case that you need to do it in general, okay? So 2 times BC, which is of course the same, but let us pretend that they are not the same. In general, you need to multiply the numbers in. So the first pair becomes 4, 12, and 0, because I have multiplied 3 by 4, and I have multiplied 3 by 0. I get this number. Then I multiply 2 inside, it becomes 8 and 0, and then I subtract them. So this means that finally my vector 3 times dA minus 2bc is equal to 4 and 0 again. Okay, and then this is what the first part of the problem. The second part, we are also asked to calculate the magnitude. So if I remind you, do you remember that if I have a vector A, V with components A and B, last time we learned that the norm or the magnitude of the vector V is used Pythagoras. We can use Pythagoras theorem to calculate it in this way. So that is also one formula we had before. So now I use this formula to calculate this magnitude of this vector. So we will have that the magnitude of 3dA minus 2bc is equal to square root of the first component 4 to the 2 plus the second component 0 to the 2. But this becomes a square root of 16 plus 0, which becomes a square root of 16, and then it becomes 4. So the length of this vector is actually equal to 4. Okay, so that was finally the final example on vectors. It was a little bit unfortunate, sorry for that, but this is hopefully everything is clear. That was just a very unfortunate thing that I chose random numbers, but it gave rise to exactly the same vector all over again. But the idea hopefully is clear, yes, is it?
Yes.
Okay. So now let us start the notion of functions. We can go to the next page. So finally, we want to talk about functions here. So functions is actually, the topic of functions is a very, very important notion in mathematics. So you need to learn it very good. I deviate a little bit from the book because I think this would be necessary to learn these stuff as well when you are dealing with functions. Then we can continue to the exercises in the book. So one terminology that I want to use when I am talking about functions is the notion of a set. Yes, so what do I mean by a set? So you can use the word collection or a group, but a group of objects or a collection of objects in mathematics is usually called set, a set. Okay, so when I say a set, so by the word set, I mean a collection of completely specified objects. When I say objects, it means that they could be numbers, they could be letters, they could be objects like pens, pencils, cars, I don't know, whatever you like. So a collection of completely specified objects. By completely specified means that you need to make sure that everyone understand what you mean. What do you mean by those collection? For example, if I say a set of some integers, this statement is not a good description for a set. Yet, so I'm not allowed to use this. So not acceptable. Why? Because the objects are not completely specified. For example, if I say I have a set of some integers in mind, and then I ask you, do you think that 1 is in my collection, 2 is in my collection? You cannot answer because it is a little bit ambiguous. It is vague, yes? When I say a set of some integers, it is not clear which integers I have chosen and which integers I haven't chosen. So you need to avoid these kinds of statements when you use the word set. But on the contrary, you can use a completely valid argument. You can say the set of all prime numbers. This is a good, this is acceptable. Because, for example, if I ask you, do you think pencil is a member of this set, is a member of this group? You would say no, because the set consists of all prime numbers and pencil is an object which is not a prime number, so definitely that pencil does not belong to this set. If I ask you square root of 2, do you think a square root of 2 belongs to this set? Immediately you would say no, because a square root of 2 is not a prime number. Prime numbers should be integers, should be natural numbers actually, and a square root of 2 is not a natural number, so it is not a prime number. On the contrary, if I ask you what do you think about 7, you can immediately say that 7 is a prime number and it belongs to this set, it belongs to this collection. Might be I ask you a big number, okay? For example, I ask you, what do you think about 7,743? Do you think that this belongs to this set or not? You cannot immediately answer that because this number is quite big, but something is clear. If you investigate and put some time on it, the answer to this question is either a yes or no. You will not be in a limbo situation that cannot answer. So you see, if I ask the same question for this description, it doesn't matter how much time I give you, you will never able to answer this question yes or no, because I am being ambiguous in describing my set. I have written a set of some integers. So you see that it is not clear how you need to confirm that this is a member of set or not. So you see, what I'm trying to say is that might be at the moment of discussion, you don't know something belongs to the set or not, but it is clear that the answer is either yes or no. Okay, there is no such a situation that we cannot check that this is in the set or not. So I hope that I could make myself clear. There is a big difference between this way of expressing a set and this way. In mathematics, this way is not acceptable, so you need to throw it away, but this one is acceptable, and we can talk about those sets. Okay, so that is enough. So this is important to know, that a set is a mathematical terminology meaning a collection of completely specified objects. Now, if you want to talk about functions very abstractly, it's a very simple notion. Assume that you have two sets. So for example, I have one set here, a collection of objects. So let me call it set A. And then it contains some objects in it. For example, I have objects, for example, let us call it A, B, let us use letters here, C, D, E, and for example, F. So these are, for example, the collection of objects that I have. Assume that you have another set. You call this set B, for example. This also includes some points. So let us use other letters. For example, Greek letters here. For example, we have alpha, we have beta, we have gamma, I don't know, we have theta, we have sigma, we have rho, and other stuff. And so we can add one more. Let me just add one more to it. So lambda. If I start assigning objects to the objects, so let's see, I want to assign objects from B to objects from A. So for example, I can draw an arrow like this. I will take an arrow from here. So let me change my color. So I can draw an arrow from here to beta. Okay, so it means that I am assigning beta from the set B to this particular element A from set A. I'm just assigning, I'm just playing a game, okay? There are some conditions, I will talk about them. So let me continue. I have to continue. For having a function, I have to specify the situation of all these points that you see in the set A. I need to assign these to the ones on the right. So for example, you can decide to assign B to theta. You can choose to assign C to, again, theta. You can choose assign C to sigma, assign A to rho. I don't know, finally, you can decide to assign this to gamma. Okay, so I'm just playing a game. This kind of assignment is called a function from the set A to the set B. Okay, so I would say that this diagram represents a function from A to B. So that is the idea. But one thing is very important. First of all, you cannot miss one of these points. You have to assign to every point in the first set an element from the second set. This is not an obligation for the second set. You see here, I have a point gamma without any arrows actually connected to that. Yes. So this is an obligation that you need to, I don't know, to draw an arrow from every point that you see in the first collection. The second and the most important thing is that you are not allowed to draw more than one arrow from each element. Okay, so this diagram here actually shows a function, but if I draw a diagram like this, let me just try to fix it somehow. So assume that I have here a collection of objects A, another collection of objects B here. So for example, assume that in this one I have A, let me make it a little bit simpler, and C here, and then I have another points alpha here, beta, gamma, theta. Assume that you have this scenario. And then I will start, for example, connect A to alpha, connect C to alpha, okay? And then connect B to gamma. So far, if I stop here, I have a function. Yes, let us check. For every element on the left-hand side, I assigned an element from the right-hand side. So if I ask you, what is the element which is assigned to A, you definitely say alpha. If I ask you what is this element assigned to C, you see again the same alpha. What is the element assigned to B? That is gamma. Are there any elements assigned to beta and theta? No, they are left alone. So far, that is a function. If I just stop here, again, this diagram represents a function from the set A to set B. But if I draw another arrow, for example, from here to here, then this is no longer a function by definition. Yes, because for functions, I am not allowed to assign more than one value, more than one item to each one of these. So you see, this is not a function. So I would say that this diagram does not, let me write this with capital letters, represent a function from A to B, since there are two elements, two distinct. So let me write it because two is not important. Being more than one is important. It could be three. Since there are more than one element in B, namely alpha and theta, that are assigned to the same element A in A. Yes. So here, this is the main difference. So this diagram here does not represent a function, but this diagram represents a function. Okay. So this is important. So you need to understand. Let me just draw a very simple diagram here below it. For example, what happens if I have this situation? If this is A, and let me do this one B, for example. I have B here. So for example, I have point A, I have a point B, I have a point C, and let me draw this. I have alpha, beta, gamma, and theta. And then I draw diagrams, for example. I draw arrows. I will connect A to alpha, I connect C to beta. So is this a diagram? Is this a function? Again, no. Because of course I have been respecting to this fact that all of them, there is no more than one arrow coming out, but there is one single element without any arrows. So it means that I haven't assigned anything to B. This is not also possible. So this does not represent a function either, yes? This diagram does not represent a function, since no element in B has been assigned to B in A. Okay, so this is B. So I hope that you understand. This is a little bit abstract notion. So if you really want to understand the function is just a correspondence between two groups of elements in a way that you assign a unique element from the second group to each element, to each and every element of the first group. So if you want to understand function very abstractly, function is just the corresponding between two elements of two sets with two properties. First of all, every element of the first set should be associated with at least one element on the set B. And no more than one element. So I have to do, so this graphically it means that when you look at the elements on the first set, every element you should see an arrow coming out from it and not more than one. But what happens on the right hand side is not that important. For example, you see here no arrow has been added to this, so that's not a problem. Here you see I have two arrows coming into the same alpha. That's not a problem again. But the problem arises from this fact that I have two arrows coming out from A. So you have to draw an arrow from each element, and you are not allowed to draw more than one arrow from that element. It is not mentioned in this way in the book, but that is good to have this picture in mind. Okay, now I will go to what we need to know for the lesson. Okay, so here, let me also talk a little bit about these terminologies here before leaving this session. This set here, this set, the whole set A is called the domain. Okay, the set B is called the codomain. Okay, but the set of all items that include an arrow, there is an arrow onto them, that gives you the range. So for example, I don't know if I can draw it correctly here, so let me try to do my best here. So assume that I have this one. So you see alpha, the lambda and beta, and I don't know, these are inside. So you see these are the only elements so that they receive an arrow. Alpha and gamma don't receive any arrows. This set that you see here is called the range. Okay, so these are the words I want you to know a little bit about them. So the word the range, the word domain, and the word codomain. So these are the words that are very important in in the function when you are studying functions. So the domains are, the domain means the elements of the set on the left that you are supposed to assign something to them. The codomain is the collection of all items in the second set, but sometimes some of these elements doesn't receive any arrows. So for example, this element doesn't receive any arrows, this element doesn't receive any arrows. Only these elements that you see are receiving arrows. The collection of all those objects that are receiving at least one arrow is called the range. So the range is some part usually of the codomain. Sometimes it could be as big as the domain codomain itself, but sometimes, like this example, it is a subset. It is a portion of the codomain. Yes. Okay, let me just wait here a little bit. So it's not a hard thing. It's just playing with diagrams. Is there any questions here so far?
Yeah, I would like to ask. So, you say examples of where this is an example of a function from A to B, but it's not
Yes.
a function from B to A, right?
Exactly, yes. If
Okay.
I want to say a function from B to A, either I should draw the diagram for B on the left and the diagram of A on the right, or I should draw arrows from B to A. But this
Okay.
is common in mathematics, that always the domain set is being drawn on the left. It's not mandatory, but this is common. And this codomain set is being drawn on the right. And then we say this represents a function, if it really does, a function from the left, which is the domain A, to the to the set B. I don't know. Could I answer your question?
Yeah, I have an so like a function can't then be from A to B and B to A simultaneously then, if I understand it.
No, it
Okay.
cannot be simultaneously. But we can also talk about an inverse function, but that is a different story. That's not at the level of the lesson. But right now, no, I cannot have a function simultaneously from the left because the direction of arrows are important. If
Yes.
I draw a diagram for a function from A to B, the name is on it. Yes, I am drawing arrows from A, actually initiating from the elements of A, and they are going to elements of B. So the direction of arrows shows that this function should be a function from A to B. Yes.
Oh, but look at the chat.
No, chat, it's very hard for me to track the chat because when I am doing it with my iPad, I concentrate on this one. You need to assume that this is a normal classroom and just talk to me, okay? In normal classrooms, we do not chat, do we?
Okay, Alex asked the question in the chat. Should I read it?
Yes, you can.
What happens if there is more elements in set B than set A?
Now, this is the case, isn't it? There is no problem. You need to, so let me just give you some examples. I don't want to spend so much time because this is completely absent in the book, but this is the really real way of understanding functions. So you see, functions are really very elementary things in our head. It's just corresponding elements from one group to elements from the other group. If you think a function of this form, we are actually dealing with functions in almost all our life. So let me give you some more examples. So if I understood correctly, so how many elements are there? 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5, 6, 7. And it has already happened here. So I think this is the questions for Alex, isn't it? So here, how many elements you see in B? 1, 2, 3, 4, 5, 6, 7. How many elements you see in A? 1, 2, 3, 4, 5, 6. So the number of elements of B is more than the number of elements of A, but still I called it a function, yes? There is no exact relation between the number of elements in these two groups. For example, this was a function and the number of elements in B was bigger than the number of elements of A. We can also assume, let us go to the next page. For example, let me draw another one. So here, for example, I can take this one A. Let me give you simpler diagrams that you can focus, yes? So let me call this one A and let me this one set B. For example, here I just put alpha, okay? So, and then I draw my diagram like this. Okay, so that was the name A. And then, for example, yes, for example, I assign A to alpha, I assign B to alpha again, I assign C to alpha. So let me see. If I stop here, does this represent a function?
Yes.
No. One condition is met, two conditions should be met. First of all, for each element you see here, an arrow should be coming out of it. The second is that there shouldn't be more than one arrow coming out from each element. The second condition is met here because there are no more than one arrows coming out from any element, but there is one element without any arrows coming out from it. So if I stop here, this is not representing a function. If I want to make it a function, I have to add this arrow as well. So here, if I ask you, is this a function? Does this diagram represent a function? The answer is yes.
Yep,
Because
this
first of
one
all,
does.
every entry, every element you see here, from every entry you see here, there is an arrow coming out. Is there any entries with more than one arrow coming out of it? No. So this means that this is a function. And you see here, I have 3 elements. Here I have only one single element. So that is also a function. So let me write it. A function. So this is also possible. So you see that here the number of elements in A is bigger than B, bigger than the number of elements of B.
Babak, I have a question.
Yes?
Can elements in A be assigned to more than one set?
No, at the time, if I talk about one function, yes. For example, you can have another you can have another set. Let me change my color here. For example, I can have this situation. I could have another set here, call it C, and then for example, I don't know, we can have different elements here. Let me call them numbers, by the way. 1, square root of 2, 3, and 5. Yes? Here, this is one function. A function cannot simultaneously be assigned to more than 2 codomains. A function is a rule that assigns elements to domains from its codomain. If I change the codomain from B to C, of course I can have a function situation again, but that is not the same function. Yes, when I talk about function, what you need to imagine, you need to imagine 2 sets, okay, and some arrows between the elements of that particular 2 sets with these properties that I just mentioned. I can consider this A with a different set. I can draw some arrows. So let me, for example, change my color here. Let us make it, for example, black. Then I can, for example, start attaching this to this. And then I can connect this one to square root of 2, for example, and this one to 5. Yes. So if I give you some situation, this represents 2 functions actually. One function, these red arrows, and this purple circle, and this green circle. This is one function from A to B. But if you consider these black arrows, yes, then this would represent a function from A to C. They are not the same functions. When you say a function, you have 2 sets and you have a set of arrows. connecting these two elements, the elements of these two sets in a way that I just defined it for you.
Okay, so you can't have A simultaneously connected to B and C. Gotcha.
No. So if you do this, this is not one function. This diagram that I just drawn here represents two functions. One function from A to B, another function from A to C.
Yeah, thank you.
You're welcome. So let me here, for example, let me make this clear a little bit. So yeah, this is a function from A to B. This part might be, this part is a function from A to C. Something like this. But here, if I ask you, what is the domain of this function? The domain of this function is again this collection. If I ask you what is the domain of this function, the domain is exactly the same collection. If I ask you what is the codomain of the first function, you would say this green collection is the codomain. If I ask you what is the codomain of the second function, you will see this blue one is the codomain of the second function. If I ask you what is the range of the first function, the range of the function is again this set. Yes, because this element is the only element of this set and it is receiving arrows. Okay, but if I ask you what is the range of the second function, then you would say that the range of the second function is this part which is receiving arrows. 1 square root of 2 and 5. By the way, in mathematics, we do not, if you want to think abstractly, so we say A is the set, you denote it in this way. You have to use curly brackets. What are the elements? Are A, B, and C. So these are called elements, A, B, and C. And if I ask you what is B, B is the set consisting of one single element, alpha. And if I ask you what is C, C is the set consisting of 4 elements, 1, square root of 2, 5, and 3. This is the way that we write in mathematics instead of draw them. The graphics is good because we can visualize things, but at the abstract level, this diagram is representing this set in mathematics, and it is important. This is the punctuation rule. For representing a set, you have to use curly brackets, and then you need to write the elements and separate them with commas. Okay, so here this is an abstract way of writing it instead of graphic. But the idea is very simple. I have two collections of objects. I want to associate objects together with these properties, that I am not allowed to associate each one of these elements to more than one element from B, and then I have to assign at least one element from B to every element from A. These two conditions should simultaneously be met, so then I am able to call that diagram the diagram of a function.
Babak,
Yes?
wasn't one condition for a set that it needed to contain 2 or more objects?
No, the set can be in principle even empty.
Ah, okay.
And that set is called the empty set. I don't want to bother you that much about that. Talking about sets a little bit properly is the topic of Math 5. But the idea is very elementary, so it is tangible to everyone in principle. Yeah, I'm just playing around with shapes, so that is very easy to understand. But in principle, the number of elements in a set can be even 0, and that is called the empty set, and it is denoted by this one. So if I ask you what is the empty set, you open the curly brackets, There is nothing that you can put in the empty set, and you just simply close it. And that's called the empty set. Okay? But of course, sets could be quite huge. For example, the set of real numbers R, including all possible numbers that you can imagine. Or even, so for example, the set of natural numbers n is, you see, I have already used these curly brackets somehow, I remember. So you start from 1, and then the next element is 2, the next element is 3, the next element is 4, but it will never end. It continues forever. This set is called an infinite set. But a set like this, if I ask you how many elements do you see in this, this is 1, 2, 3, 4. When you can count the number of elements in a set, and that number is a natural number or a non-negative number, non-negative integer, sorry, then that is called a finite set. So finite, infinite. So these are terminologies in the set theory, but I don't want to bother you about this, but I just want to mention that if you want to think about the function abstractly, this is the way that you need to think about the function. Okay, and then so here, if I let me ask you, for example, and by the way, the functions are denoted by small English letters usually. So for example, and then we write it like this. For example, if you want, I can call this function the function f, and then I put semicolon in front, and I put a, and then I put an arrow in front of a, and then I put b. This should be read in this way. F is a function from a to b. I called this function, this part, I called this one f. So for example, if you want, you can write f on top of this. But this function, for example, from A to C, I can give another letter to it. Usually we denote it, for example, by English letters F, G, H, and so forth. So here I can write that G is a function with domain A, but its codomain is C. Okay? Here, I can ask you what is the domain of the function. This is the symbol we use. We put a D for domain and a subscript F for the function name. So this is called the domain of function f. If I ask you what is the domain of function f, you can answer it in two different ways. You can say that this is the set A, or if you want to, you can mention its elements A, B, C. Okay? If I ask you what is the codomain of f, CO, yeah, so this is a little bit more complicated symbol. So codomain of f, they denote it by this. And then this is, you can call it B, or if you want in this case, it is just a set consisting of alpha. And if I ask you what is the range, so the range is denoted by R for range and then sub F. Codomain is not mentioned in your book, but the domain and the range are mentioned in your books, not in abstract level, but in a little bit. I will come back to that in a few moments. Okay, so but if I ask you what is the range of F here, so then becomes what? Then it becomes alpha. So let me write it. You can answer B here, or you can answer alpha. Okay? But let me just repeat these things for the function g. If I ask you what is the domain of function g, you can answer it in two different ways. Either you can give me the name of my set, or if you want to be more explicit, you can mention the elements and say this is A, B, and C. If I ask you what is the codomain of this function g, you can say that the codomain is C, and if you want to, you can write the elements 1, square root of 2, 3, and 5. But if I ask you what is the range, here in the previous example, the range and the codomain were the same. But here the codomain is this, But if I ask you what is the range, I am asking you which of these elements are receiving an arrow. All these elements are receiving an arrow except element 3. So the range should be, you cannot write C, you need to explicitly mention. One of them is receiving arrow is 1, another one which is receiving arrow is 2, another one which is receiving an arrow is 5. So this is the range of this function now. Okay? Any questions? Okay. And then one thing that I just want to mention this before leaving is the value of a function at a point. This is the terminology we use. We say the value of a function, but when we talk about a value, we expect that this should be a number, but this is not the case. Usually when we talk about the value of a function or the image of a point. So let me talk about that one in the next diagram. So for example, let me consider this diagram here. So let me make it a little bit bigger. So this is my collection A. So let me put some points here. So let me have A and then B, C, D, E, F. For example, the first collection contains these points. And then let me go to the next collection containing, for example, let me choose letters, Greek letters here. So alpha, beta, gamma, theta, rho, lambda, and let me put another one, sigma. Okay, so now let me draw some arrows to to represent a function for you. So let me choose this one. For example, assume that I decide to associate lambda to A, to assign lambda to A. So for example, this one, and then we decide to associate alpha to A. Yes. And then, for example, I associate this one to this. And then I can do, for example, this one. Oh, let me first do this and then do this. Okay. So far, is it a function? No, because there are some elements that I haven't assigned any elements from B to them. Okay, so I need to continue assigning this. But for example, let me do this. I assign E to the same lambda here again. Let me fix it. So I assign E to this one again. Let me assign F to sigma. Oh, I don't know why this is doing this to me. Okay, let me. Oops. Okay, forget about this. Let me change F. So this is F. Assume that this is F. Okay, and then I put the arrow here. So for example, let me give, first of all, do you agree that this diagram represents a function? Yes, because first, I have two collection of objects. I am drawing arrows between these objects with two properties. First of all, every element here is assigned to one element here. So every element, there is an arrow going out from each one of these elements, one condition. The second condition, no more than one arrow is going out from each object on the left. So this gives me the graph, the diagram of a function. Let me point out that some of these on the right are left without any arrows. This is no problem at all. And one of them is receiving more than one arrow. That's not a problem at all. So be careful, don't get confused here. What is very, very important is that you draw an arrow from each element, but not more than one. What happens on the right-hand side is not that important. Of course, we have different types of functions. One of them, for example, is called injective function, the other called surjective function, and bijective functions. This depends what happens on the right-hand side. But you don't need to be worried about those at all. You need to be worried about what is happening on the left-hand side. So let me call this a function. For example, let me give a name. It doesn't matter. So this time, let me choose the name capital F. So this diagram is the diagram of the function f. If I want to write more explicitly, I would say that f is a function from A to B. Okay, so f is a function from A to B. Okay, and then I can ask you in this way. I can say that what is the image? This is the word that you need to remember. What is the image of A under the function f? This terminology means what is on the right-hand side of this arrow coming out from A? So simple as that. So what is the image of A under the function f? You see, you follow the arrow and you get lambda. So you say that the image of A is lambda. There are two ways to express this in symbols. We can say that A is sent to lambda and put the name of the function on top of that. This is read in this way. If the function f sends A to lambda. This is one way of reading this. Or you can say that the image of A under the function f is lambda. That is also one way of reading this. So this is read in two different ways. But there is also a better way of expressing this here, because you have a lot of things to do. It is common in mathematics that this symbol, yes, is being represented in this way. We say that if acting on A gives me lambda. Okay, so and then I will read it in this way. F of A is equal to lambda. This is how we read this symbol. So this symbol means exactly the same as this one. This is also given sometimes in your book, but this is the most common one. And then we use equality. We say f of A is lambda. So this means that if the function f, this diagram, associates A with lambda. Okay, so for example, in this symbol, if I want to ask you another question, it is very simple. If I ask you what is f of B, what is the answer? So what is f of B means that I need to follow the arrow for B and see what is the image. The image is alpha. So f of B is equal to alpha. So let me write all of them. I can ask you what is f of C. What is the answer? F of C is equal to theta. I can ask you what is f of D. You would say is beta. And if I ask you what is f of E, you again answer the same lambda that you answered for f of A. This is expectable because this lambda is receiving two arrows. One is coming from E, another one is coming from A. And finally, if I ask you what is f of f, you would say that this is equal to sigma. Usually, even though lambda is not a value, is not a number, is a letter, we say that the value of the function f at point A is lambda. This is some terminology you might see somewhere. So when we say f of A is equal to lambda, sometimes you hear this sentence even though technically lambda might not be a number even in the first place. Yes, we can say that the value of f, I mean the function f at a is lambda. Sometimes you see this, but if you want, usually if you want to really be very precise, for the cases where this is a number, you can talk about value. Otherwise, it is better to call this the image. This is better. So this is exact. So I don't put the quotation mark. The image of a under f, under the function, if you want, I can emphasize it, under the function f is equal to lambda. Okay. So let me ask you, what is the domain of this function? So let me finish everything here for this one diagram, and then we go to what we need to learn for the exams and things like that. But this picture, having in mind this picture for the graph, for the function, is very important, I think. I don't know why they haven't talked at all about this, but so let me write the other. If I ask you what is the domain of f, do you remember the symbol? You put a capital D for domain, and because the name of your function here is also capital F, you write the D sub f. Okay, what is the D sub f? D sub f can be written in two different ways. Either you can name your set, which is A, or if this is possible, which is in this case possible, let me explicitly mention all of them. But if you want to explicitly mention all of them, you need to respect the rules. This should be a curly bracket. Parenthesis is not acceptable. This is not acceptable. You have to use the curly brackets. And then I have A, B, C, D, E, and F. If I ask you what is the codomain, for the codomain, you don't need to be worried. This is not mentioned in the book at all, but let us do that. What is the codomain? You can do it in two different ways. Either you can write the name of your collection, the name of your set, or in this case, it is possible you can actually list all of them, but you have to put them in curly brackets and separate them with commas, not, for example, with dashes or something. You have to respect the rules. And then rho, lambda, sigma, and then you close it. But if I ask you what is the range of your function, what is the range? The range is that part of the codomain which are receiving at least one arrow. Okay, so it means that gamma is not in my range, even though it is in my codomain. Rho is not in my range. So every other members are actually in the range. So the range is alpha, beta, theta, lambda, and sigma. So that is also the range of this function. So any questions? Okay, good. Now let us go and start doing some functions in mathematics that we are dealing with, because in mathematics that we are dealing, we are usually working with numbers, okay, instead of abstract objects. So here, of course, I use letters, but these letters can represent whatever you like. These could be real objects, for example, pen, pencil, or whatever they can be. I don't know. For example, this can be pens. So you can say, I can have a set of objects here, and these are the prices of those objects. For example, pen, this should go to a number, for example, 5. It means that the price of this pen is 5 crowns. And then, for example, a car might be, I don't know, 500,000 crowns. So it means that these in principle can be any kind of objects that you like. Objects including numbers, whatever you think. That's a correspondence between a group of things and another group of things. Okay, but now let us go and talk about what is given inside the book, which is more or less the same thing. The functions are, so let me start with an example, and then let us see how we can think about this again. So example, usually you face these kinds of examples. So let me write this. Consider the function f with the following rule. So I am intentionally writing the sentence in this way because I mean something. I write f of x is equal to x squared, as simple as that. Okay. So what does this mean? It is better to think it in this way. Here, it is better to think that f is an operator, is like a machine that you give an input to it, which is a number, and this one is the output that you expect from this machine after this input is being processed. So what I mean, you can assume that you have a box here, yes? And what you do, you send x in, and what comes out is x squared, yes? So let me write it in this way, it's better. So let me put x here. So you send x here, some operation is being done in this box, and what you get out is x squared. This box itself is f. Okay, so some books, it's not correct 100%. They say the function f of x. You see, f of x is not the function itself. F of x is the product when the input x is being processed by the function itself. So if I want to draw a diagram that you need to have it in your head, assume that you have a box here, a machine, some kind of operator. You need to think in this way. You send x in. If the name of the function is f, what you get out, it is called f of x. So for example, I don't know if this is a meat mincer, if I remember the word correctly. So if this is the meat mincer, so you put blocks of meat here in the meat mincer, and what you get out is the minced meat, okay? But nobody confuses the minced meat with the mincer itself. Mincer is that apparatus that is mincing the meat. This that you put as input is the meat, okay, the block forms of meat, and then what you get out as a product is the minced meat. F of x plays the role of the minced meat. X plays the role of that blocks of meat. F itself, which is your function, is the mincer. So it is not, so I understand that, I hope that you understand that you cannot say f of x is the same as f. F of x is your product. F is your apparatus, and they are not the same. So even though some books write the function f of x, it is not 100% correct. You should say the function f with this rule, that if f acts on x, it gives you x squared. So this is something that I want you to know. Okay, so let me put this in a box here. So this is the picture that you should have in mind all the time when you are dealing with functions here. Okay, a function is an operator, is a machine, takes an input from you, do some process on that input, and gives it back to you. Something gives back an output to you. For this function, it takes a number from you, square it, and give it back to you. And then what I want you to understand is that the name that you use for the input is totally irrelevant. It doesn't matter what name you use. For example, I can say that f of a is equal to a squared. This gives me the same information as here. But what I have done, I have changed the name of my input to be a. I can write f of beta is squared. So what you understand from here, you understand that this function is a squaring machine. What you understand from here is exactly the same information. If I ask you what is the role of f, you see that f squares. So that's also the squaring machine. And then if I ask you what is this one, you will also say that's also a squaring machine. So even though I am expressing it with different letters, but this doesn't affect the definition of the function itself. From all of them, you get the same piece of information that your function is squaring the number of the input that you give in. Okay. So let me wait here. Do you have any questions? This is a little bit conceptual. It comes by time. It's not that hard that might seem in the beginning. Okay. Okay. So let me ask you
one question.
Yes.
Why do you use the word meat mincer to describe the machine? Like I don't understand. What's the relation?
No, I don't know. I just get I had this example in mind. So I mean, yes, you can. So even I mean, the notion of function is completely generic. It shouldn't only think about numbers. If, for example, I have a meat mincer here and I put the blocks of meat here, I want to understand the difference between the apparatus itself and the output, because even in many math books, you see they call the function they call the function f of x. I mean, this sentence is also used in some math books, but I want you to understand this is not 100% correct, because when you write f of x is the product of your operation. Okay. Function is the operation itself. The product of the operation shouldn't be taken the same as the operation itself. Do you understand what I mean?
Yeah, that actually makes sense.
Okay, so I was thinking that might be, I don't know if this example is misleading, you can just leave it. What I was thinking is that if you have the minced meat, is the product that you get, nobody will say that the minced meat is the same as the mincer. But when it comes to math books, some books I have seen, they write the function f of x. The correct way of saying is that you should say the function f defined by f of x equals to x squared. Might be this sentence is long and people are lazy, so they write the function f of x. It's very important, not for your lesson might be, but it is important to differentiate between f and f of x. That is what I meant. Might be that my example is misleading, sorry for that, but that is what I meant.
No, it's not misleading. It's very good. It's very useful now that you explain it.
Okay. So,
Babak, I have a question.
Yes.
Is there a systematic way to find what f is?
No, there is no systematic way. So you see exactly this again. There is no one single function that we want to systematically find it.
Okay.
So for example, this mincer is a function doing something for you. Okay. For example, here, that's also good, by the way. So you see the values that you can put in are the domain of the function. So here, for example, you cannot put metals inside this mincer, because this mincer is defined to work with blocks of meat. So if you want to draw an analogy between the domain, so I would say that the domain of this function, it means that the material that I can feed in to this machine is the blocks of meats, and what I get outside would be the minced meat. So there is no unique function. You can talk about infinitely many functions. Whatever you define here is a function. For example, let me just do them step by step, okay? Because there would be a lot of things confusing. So let me come back to this example. Consider the function f with the following rule. If I ask you what is this function, you would say this function is a squaring function. Whatever I put in, it gives me x squared back. Of course, if I want to be very strict, I have to also define what do I mean by the domain of this function. But I don't want to make it so hard for you. Implicitly, people understand that this input should be a number. Yes.
Oh, yeah, right. The function is always
But in
defined in the question.
principle, I am not allowed, because nobody, for example, this meat cannot go into this function, because what is the meaning of a block of meat to the power of 2? So you see, this doesn't work here. So explicitly, these are not talked in the book because they are just taking this for granted. But in principle, if I want to define a function, I have to give you 2 pieces of information, especially 3 pieces. I have to give you the domain, I have to give you the codomain, and I have to give you the assignment, the rule. Okay? But get used to this. Your picture of functions is not that complicated, so people talk about functions of this form, taking this for granted that your domain is a set of numbers that you can use numbers. You can use operations, numerical operations on them, arithmetical operations. Now tell me, if you understand everything, that you can save me a lot of energy now. If I ask you for this function, what is f of 5? Can you answer this?
Yes.
It's 5 squared.
Yeah,
It's
exactly.
25.
It's 5 squared. It's 25. Because you are by reading this sentence and having this analogy in mind, you interpret this as a machine, as an operator, which takes the value x as an input. The process is squaring it and give it back to you. Now I am feeding the same machine with 5. So what will I get in return? 5 to the 2, which is 25. Okay, so if I ask you another question, what is f of a? Assuming that a is also a number, what is the answer? What is the output coming out of it?
A squared.
A squared. If I ask you what is f of x plus 1? Now, so this is you need to know what is in here is the input. So whatever you see inside the first pair of brackets is the input for your machine. Here you see x plus 1 as your input. But so what would be the answer?
Within parentheses, x
It's
plus 1
x squared plus 2x plus 1.
Yeah, that's x squared plus 2x plus 1. Let us keep it for future, okay? Yes, but you are right. I will keep it like this. If I ask you what is, I don't know, f of a square root of x, then it becomes a square root of x to power 2. The answer is x. Is that clear? So as far as you have the correct interpretation for what a function is, calculations for functions is very simple. I hope that there is no misunderstanding here. But it might happen that we have more fun. We could have more fun with functions. Might be we have some functions with different rules, depending on the value of the input that you provide for your function. Okay, so this function.
I have a quick question.
Yes, please.
And this in the example,
Yes.
where is the domain and where is the codomain?
Okay, so that is what I told you.
Okay.
If I want to be explicit, I have to give you the domain itself. Because, for example, first of all, by looking at the form of this function, you immediately realize that this input should be a number, yes? Otherwise, squaring something except numbers doesn't make sense at all. But the domain could be the set of natural numbers. But there is no guarantee. The domain could be the set of integers. The domain could be the set of all possible numbers. This is a convention again. If I don't talk about the domain, you need to consider the largest set possible. Okay. If I explicitly, if you want, you're asking, let me just talk a little bit about that, even though you don't need to know all of these things. But for example, I can say the same thing and I can emphasize that my domain is N. Then if I ask you f of 2, you will answer me, it is 2 to power 2, it is 4. But if I ask you what is f of minus 2, you do not answer me, because you are telling me that you yourself is telling that the domain is N. It means that I am not allowed to put minus 2 as an input, because minus 2 should be my domain and it is not. And then if I ask you this careless question, you would write undefined. Yes, so this is very important to know. But I can have the same rule with a different domain. Okay, and then I can ask you what is f of 2, you will answer me 4 again. Here I can also ask you what is f of minus 2, you would say minus 2 to power 2 is 4 again. So you see, if I give you the domain here, if I explicitly give you the domain here, I am not allowed even to ask you this, because the inputs are coming from the domain, and minus 2 should come from the domain, but minus 2 is not from N. But I told you that convention is this: if nobody talks about the domain explicitly, then it means that the largest set possible that you can imagine would be the domain of that function. I will talk about the domains later. That is the topic of the next lesson. For example, can you talk about this? If I give you this rule, f of x equals to 1 over x. And if I do not specify the domain, you need to consider the biggest possible set to be the domain of this function. So can you tell me what is the domain of this function? I will come back and talk about this next session, but I just want to say something because it might be helping. So if I don't say anything about this, if I say that f is a function with the following rule, what you need to understand about the domain yourself. What is the domain? Can you guess? Can you tell me what's the domain?
I think it's IR.
IR, what do you mean IR?
Like the domain IR, you know, that you were above.
No. So which numbers you can fit in? For example, can I ask you what is f of 1? It is 1 over 1, which is 1. Can I ask you what is f of a square root of 2? It becomes 1 over a square root of 2. There is one number that I cannot ask you about. What is that number? Let me tell you. What is f of 0? Everyone?
Undefined.
Yeah, it's
Undefined.
undefined. So you see, we will talk about this later. So you see that the only number that I am not allowed to put for x is 0. Yes? So this means that the domain of this function is the set of all possible numbers except one number, and that is 0. And this is the way that we write it in mathematics. I say that all real numbers are allowed except one single number. Except it means subtraction. You don't need to be worried about these things because these are a little bit more advanced topics. But it means that the domain of my function should be considered this one, because this is the biggest set possible that I can imagine for this. So let me close this idea here. We will come back to this later, okay? Okay, so let me now talk about another type of function. So might be the rule of the function is not unique. Depending on the number that you are giving to your function, the function does different things to that input. For example, let me go below here and write this example. And let me change the name of the function. So I would say, let me write the proper way of writing. So let G be a function. You see, I don't write g of x. I say let g be a function defined by, so I would write g of x is equal. This is the way people write it in mathematics. They put a little bit big curly brackets around. For example, here they can say 2x plus 5, and then they put a comma, and then in front of the comma, for example, they write x is greater than or equal to 3. And then I would say, for example, x minus 1 if x is less than 3. So these are multiple ruled functions. So here, my function has two different rules depending on the input. So how should I read it? I should read it in this way. G of x is equal to 2 times x plus 5 if is implicitly mentioned in this way of reading. Some books write the word if, but sometimes you don't see if here. It means if. 2x plus 5 if x is greater than or equal to 3, and it is equal to x minus 1 if x is equal to 3. So if you want to imagine, so you can imagine it in this way. I don't know, you have a machine here, and then you send an input here, x. When the function first evaluates this number, if this number is greater than or equal to 3, it is being processed in this part. For example, assume that your function has two parts. Your machine has two separate parts. When you send an x, the function checks this value. If this is greater than or equal to 3, it will send it here, but the output that you get, I don't know, is x. This is not a good way because the output is just one single item, so it might be this is misleading. So let me just correct this picture and then do some process and send it here. And or if this is x is less than 3, this will go here, this will go here, and then this will come out. Finally, 1x will come out. I don't know, is this a good picture or not? This is called g of x. So don't be confused. You will get, so when you send an x in, you do not get two values. Do you remember I told you that if I send x, I am not allowed to have two values. Do you remember? I am not allowed to have more than one arrow coming out from one single element. If this is the case, this is not a function in the first place. A function means that you have to assign a unique value to each element. So you see, x goes in, one input goes in, exactly one output comes out. But depending on the input that you provide, the process being done internally in the machine is different. The machine acts in this way. If the value you are giving to the machine is greater than or equal to 3, this part will act. What is that part? Let me clean this and make it more clear. If that is the case, this machine will multiply your input by 2, add 5 to it, and give it out. But if the number that you are giving to your machine is less than 3, it subtract 1 from it and give it out. I don't know, this is the way that you need to think. For example, if I ask you for this function, what is g of 10? So you are sending 10 to this machine. Machine will actually analyze this 10. The machine sees that 10 satisfies this condition, not that condition. So this means that the machine will send your input to this part of the machine. Okay, so then the machine will multiply that input by 2, add 5 to it, and give it back to you. So this becomes 2 times 10 plus 5. The answer is 25. So the output for 10 for this particular machine is 25. And then if I ask you, for example, what is g of 0, then again you are sending 0 as the input to your machine, but the machine analyzes this input and realizes that your input is less than 3. It will not send this 0 to this part. It will send 0 to this part. Okay, and what is the role of this part? The role of this part is to subtract 1 unit from the input that the machine receives in this part. Okay, so this becomes 0 minus 1. The answer becomes minus 1. Is that understandable?
Yeah, if I could ask, could you like use this example with like the meat mincer, like, or is that like, does that not like work?
Yeah, might be. For example, this mice, I don't know, this meat mincer depends to the weight of the one block that you put in. For example, I don't know. Or no, the quality. So the quality of the meat, for example, if you
Yes.
have the cow meat or if you have the lamb meat, and if you want to give a price for it, for example, yes.
Oh.
This you send it to this mincer, and if this mincer, I don't know, if this mincer sees that this is a cow meat, it will do something to the cow meat and give something out. But if this is, I don't know, for the lamb meat, it will do another process to it and give it out. But at the end, what you put in this machine, you get exactly one output depending on the input that you put. Something like this. This is not a very complete analogy, of course.
Yeah, but it works. It works.
Yeah, okay.
Babak, can you
Yes.
have more than 2 separate
Yes,
conditions?
you can have any number of compartments of your machine.
Okay.
Yeah, not 2, 3, 4, 5, etc., etc. The notion of functions are very important, so I will come to these ideas again to repeat this. But let me just one thing here. What would be g of 3 itself? Can you tell me?
The above option.
Yes, the output is not the above function. What is better to say is that the function uses its first rule to process this. But you shouldn't say that g of 3 is the above rule, because the output is a number. So which number is that? Can you tell me?
11.
Yes. So you say that the machine analyzes this tree. It realizes that this will satisfy this condition for the machine. So it doesn't care. It actually sends it to this compartment, yes? And then the machine starts doing the process. How? It multiplies your input by 2 and then add 5 to it and give it back to you. As you said, this is 11. Is that clear?
Yes.
Okay, even though these kinds of examples are missing in the book, but I think they are super important if you want to understand the concept of function. By the way, so far here, how many inputs you put in? 1. How many outputs you get out? Even 1. But sometimes you can put more inputs and get more than one output. You can also put more than one input and get more than one inputs. So let me just give you some examples. You see, these are not hard things, but it will help you to understand the notion of a function, how generic is the notion of a function. This is very important. So for example, I can say something like this: let f be a function. So from now on, I always work with the biggest possible set, if possible, the set of real numbers, okay? So don't worry about the domain and codomain, things like that. Let f be a function defined as follows. So we write f. I provide 2 inputs for it, x and y, and then I say this is x squared plus 2 times y. So now I don't want to express anything more. Do you understand? Can you read this for me? So just look at this problem. Do you think that after this question, it makes sense to ask you f of 1? I just want to have your opinion about this.
No.
How do you interpret this? And is this possible for this function, ask f of 1?
No, it's not.
No.
No. How many inputs I need to provide for this machine?
2.
2.
2. One of them is called x. There is no necessity of calling it x. A will work, alpha will work. Even I can write f of box and circle. This also works. It doesn't matter. I need something to denote the first entry. I need something to denote, to communicate with you. I'm communicating with you that this x is the name of the first entry. This y is the name of the second entry. Okay, so and then you realize that this, if I give you this function, I am not allowed to ask you about this, because I'm just giving you one input, but you see that there are two inputs involved. Okay, so now I think you understand what's going on without actually me having to tell you. So for example, if this is the function, how should I interpret this function? So I should, if I want to draw this analogy, I have, I don't know, a machine, something like this. Okay, I have to send two values here, x and y. This is my machine. What is coming out? Can you tell, according to this machine? What should I put below this arrow?
The function.
Either I can write f of x and y, or I can write x squared plus 2y. So you see, this is exactly one machine, one single machine, but it is taking two inputs from me. The one on the left is called x. I am calling it x myself. The one on the right, I am calling it y. I send them to this unit, to this operator. This will give me back x squared plus 2y. How should I interpret this? This machine will take the left-hand side entry, square it. It will take the right-hand side entry, multiply it by 2, add these two results internally, and finally gives me this back. Is that clear?
Wait, you said single function, so you can have more than one function at once?
No, this is not more than one function.
Well,
again, you see.
You said single function, so is it possible to have more than one function? Because it seems weird.
No. Each machine is one function.
Yeah, but can you use multiple machines for this one?
Yes,
definition?
you can use multiple machines, and then we'll talk about that. For example, the product of this machine can be sent to another machine. Another process is being done on that input, that output, you see? That is another issue. I will come back to this later. That's the composition of functions, one after the other.
Okay.
But every machine that you see is just one single function. But I mean that you need to broaden your point of view about functions. The functions are just machines taking inputs from you, giving outputs. Might be this function takes one input, it has one internal structure, gives you one output. This is the simplest possible function. One input, one internal structure. I mean that there are nothing like this. Here I have one input, one output, but I have two internal structures. Okay, the important point, so you will see that we have the situation in this case. I have two inputs, one internal structure, it's a unit, and then I have one output. So let me ask you this question. If I ask you what is f of 1 and 2, 1 and 5, what is the answer? And if I ask you what is f of 5 and 1, what is the answer? Answer me the first question first. How do you calculate f of 1 and 5?
1 plus 5 equals 6.
No, the function. The function.
Sorry, I forgot which function it was. Sorry.
Yeah, this function f, yes. So this means that this becomes the first one to the 2. The first input on the left is 1,
Plus 10.
and the The other input is 5, so I multiply that one by 2, and then I add them. So the answer is 11. But what is the answer to the next one?
27.
Yes, because how? The first number on the left squared plus 2 times the number on the right. This time it becomes 25 plus 2, and as you said, it is 27. Is that clear for everyone?
Yes.
Yes. Okay. So for example, let me give a little bit of another example. So example, we are finished here because I lost the track of time. I hope that you are not tired because this is a very important lesson. So here, another function I can talk. So I would say let G be a function. Let me change the letter. Don't think that it's always, let me call it H. Let H be a function defined as follows. H of x, y, z, and t is equal to z. Okay, is that understandable? If you want to draw some diagram in your head, if you want to visualize it in your head, how many inputs this function takes from you?
4.
4.
4.
4.
But how many units are there internally in your function? How many units are there? There is how many rules you see here? That is the meaning of my question. So input x, y, z, t. And then of course, I will get an output. And this is the machine H. I will send these outputs. What actually this function only cares about which one?
Z.
Z. So it doesn't care about other inputs. It gives you Z back. So this is also some sort of function. You send 4 numbers to the function H, but this function only cares about the third one. So now answer me, what is H of 1, 2, 3, and 4? Is it a sensible question? Yes, because
3.
how many inputs I
It's
have
3.
provided? Yes, exactly. That is 3. Now answer this question. H of 5, 9, 3, and 4.
3.
3.
Again 3. You see? So this way of thinking about functions is very helpful. This picture is missing in the book somehow. I don't know, for some reason they might think that this is hard, but this is not hard at all. This is the way that actually you understand it quite well. So remember, you see, I am differentiating. Always put the name of the function. You see, I don't write H of x, y, and z, and t. I always call it the name of my function. This is the operator. And the inputs are giving in this form, and I have one input. I can also have more than one output. Okay, but I don't want to talk about that right now. I will start next session from this part to talk about functions. Okay, I have to process this video, then I will upload it on YouTube. Okay, so it takes some time, but it will be there. I will also put the PDF file of the notes both in the Google Drive and in the description below that video that I'm going to upload. Okay, I hope that you understood a little bit about this, but there are many interesting things coming for the next sessions. We will talk about this and finalize the functions. It's very, very important to have a good understanding of what a function is. It's completely general, a generic idea. Okay? Any questions? So let me stop this sharing and also stop recording.